Welcome to another SAMPE Technical Committee webinar. SAMPE is the Society for the Advancement of Material and Process Engineering. My name is Raj Manchanda. I'm the Chief Technology Officer, and I'm accompanied by Ms. Rocio Figueroa, Program Manager, and Ms. Alex Principe, Technical Programming Coordinator. Today's featured speaker is Dr. Anoush Poursartip. He is professor at University of British Columbia and director of research at Convergent Manufacturing Technologies. The presentation will be on process simulation of thermoplastic composites. In the chat, please introduce yourself to the group. Add your name, your organization, your job position or title, and where you are geographically located in the world. Again, in the chat, please enter in your name, your organization, your job position or title, and your geographic location. Thank you. SAMPE offers technical committees in advanced manufacturing, bonding and joining, materials for extreme environments, sustainability, and thermoplastics. Today's webinar is sponsored by the Thermoplastics Technical Committee. We urge you to join a technical committee of your choice on the 365 platform. The technical committees produce the State of the Technology Industry Report, a useful resource that is available on the SAMPE online store at no charge. Membership in SAMPE has significant value. If you have some questions about membership, my colleague, Ms. Kelly Chin, is available for your questions. Membership includes discounts to upcoming events, access to SAMPE journal papers, and access to a digital library. SAMPE 2024 is coming up very soon, and we urge you to scan the QR code to learn more about the excellent exhibition and technical program. I'm going to introduce my colleague, Ms. Chris Locke, Director of Marketing and Membership at SAMPE, to discuss a little of the SAMPE Long Beach program.
Thanks, Raj. Hi, everyone. I'm Chris Locke, Director of Marketing and Membership Services here at SAMPE in beautiful Diamond Bar, which you can see behind me here in California. I'm going to share my screen and, Raj, I can't share my screen until you stop sharing. There we go. Thank you. Okay, and just as a reminder, we are recording this session. So I just wanted to talk real quick about registration for our SAMPE Long Beach conference. The discount for early birds is ending in 5 days on the 25th. So please register. It helps us as staff know who's coming and where you're all coming from and so forth. So that's important. But more specific to this group that's on the call, I wanted to share with you some of the great thermoplastics papers and presentations we'll have in Long Beach. We'll have over 18 sessions. These are just some of the papers that are going to be presented on thermoplastics. There's a whole lot more in other areas as well, but just in thermoplastics, look at this. It's amazing. Starts on Tuesday, goes all the way through Thursday. So lots of good material here for you. We want you to come. Long Beach is going to be fabulous. It's going to be warm and sunny, no rain, I promise. So as I mentioned, the early bird rate ends on March 25th. And here I have just a few of the ways that you can be engaged with us in Long Beach. Everything from the full premium conference rate on down to just if you want to go into the exhibit hall and check things out, we have that as an option as well. But as Raj mentioned, we do have membership, and there's a significant savings to joining us in Long Beach if you become a member of SAMPE. So the rates are right here on the screen. There's something for everyone, and it's a great deal, great savings. So definitely encourage you to be a part of SAMPE. And then this is SAMPE 365. It's one of our areas that we engage in to chat and engage. It's kind of like LinkedIn on steroids for folks. Right. So yeah, that's everything. And I don't know how to
Great.
stop sharing my screen now.
No, thank you, Chris. And the technical committees are located under the groups feature. I'm going to now pass it
Right.
over to Dr. Julieta Baroda Robles, who is co-chair of Thermoplastics Technical Committee. David Leach is also co-chair of the Technical Thermoplastics Tech Committee, but Julieta will be moderating today's webinar. So thank you, everyone. Thank you, and please continue to introduce yourselves in the chat. Thank you.
Thank you so much, Raj. And as Raj mentioned, I've been co-chair of the Thermoplastic Committee with David Leach. So I encourage anyone to please join us, even if it's for one meeting to see what it's all about. We have different work that we're doing, including working on a supplier database, for example. We have Literature Club where we discuss the latest papers on thermoplastics. And also something to follow up with Sampi that I wanted to bring up, we're going to be hosting a panel on welded assembly and repair of thermoplastic composites, which is going to take place on Wednesday, May 22nd in the afternoon, late in the afternoon. So more details will be posted on the Sampi website. And with that, I want to introduce Professor Anoush Poursartip. And as it was already briefly mentioned, he's a professor of materials engineering at the University of British Columbia, where he's the director of the Composite Research Network and co-director of the Composite Knowledge Network. Anoush is also part-time director of research at Convergent Manufacturing Technologies. Anoush has always been interested in the development, validation, and application of simulation to reduce the risk, cost, and time in developing new composite materials, processes, and products. So I encourage anyone who has any questions throughout the talk to please put them in the Q&A. I'll be moderating the questions at the end. And also to let you know, the recording is going to be available in about 3 weeks or so, and you should be able to get the link afterwards. And with that, please, Anoush, go ahead.
Thank you very much, Julieta. Chris, could you be so kind as to stop sharing so I can share?
I would love to, but I seem to be having trouble figuring out how to do that. Oh, here it is. Hold on. There we go.
Lovely. Thanks. If somebody could confirm you can see my screen.
We can see your screen, and it's in presentation. It's all good.
Thank you so much. Thank you so much for giving me the opportunity to share with you a little bit about process simulation of thermoplastic composites. So I'd like to start off by acknowledging what I'm going to present to you is work directly and indirectly related to the work of many generations of both UBC and Convergent researchers and colleagues. In particular, with respect to thermoplastic research, you can see a number of names there. They're the ones who did all the hard work. I get the privilege and pleasure of sharing that with you. And of course, we've done this over the decades with a whole bunch of partner organizations, funding agencies, collaborators. And again, specifically today, the collaborators that have truly contributed to the work directly are NRC, DLR, and Torre. And finally, this is a huge topic. So I really want to emphasize that I can't provide you with a comprehensive review. And so what you're going to see is an unavoidable bias to our own work. So I just want to sort of declare that right up front. So the way I'm going to do it, I'm going to talk to you a little bit about process simulation in general. Then I'm going to talk about how do we create a virtual material, how do we create basically a material card for thermoplastic process simulation, crystallization melt kinetics, mechanical property development, touch on degradation and weld quality simulation, and then a couple of case studies, acknowledging that we don't have a ton of time. And I was told quite rightly to allow as much time as possible for questions. Technically, this is a presentation to the Thermoplastic Committee, though I can see that we have quite a few other attendees, which is lovely. So I'm not going to go into why thermoplastics in any great detail. The one that I think really is kind of relevant to the simulation stuff that makes it different is that there's a huge interest in fast production rates and, of course, automation. In terms of challenges that then lead into process simulation issues, we have the issue that we have high processing temperatures, and that means really that we have a fairly small window from where, say, the viscosity of the matrix is low, and you get into degradation problems. And of course, what we're trying to do is avoid the defects that detract from the value of the material. So a little bit of thinking about physics-based process simulation. Physics-based modeling founded very much on our understanding of the causality of events. We can touch a little bit later if you are interested in the chat about machine learning and so on. But physics-based modeling is something that actually allows us to have confidence in the predictions. And obviously what we do is we understand the phenomena of interest. We then turn those into mathematical representations. Really important point to make with composites manufacturing is that you really need to capture the whole system, not just the material and the shape of the part, but you've got to bring in the tooling, you've got to bring in the equipment. And in general, the process is then the boundary conditions on the process. The more complex the system, the more useful process simulation becomes. And you really should, if you're interested in using process simulation, really apply it at all stages of the life cycle of a product. And in fact, the best place to use process simulation is before you build your factory, before you build your equipment, because that is one of your biggest sunk costs with the longest lead time. So a typical workflow, which applies to both thermosets and thermoplastics, is that you basically walk through the factory and you model the whole thing. The first one really doesn't apply to thermoplastics, but it's basically the debulking step in the thermoset process. Then we get into this important and dominant modeled step, which is understanding the thermal and phase transformation behavior of the system. This is where we understand that getting heat into a part and out of the part is slow because it's a polymer-based material. And of course, the phase transformation, be it cure, be it melt crystallization, is obviously the key thing we're trying to control. Based on that, we get material properties that allow us to understand how the material will flow, how it'll compact. If it's a weld, how the weld will heal and cease to be a defect. And then once the material solidifies, because you're cured or because you go cold again, you start developing stresses which lead to process-induced deformation, or if they're locked in, give you residual stresses that affect your mechanical performance. So specific to thermoplastic process simulation, we need to acknowledge that that desire to go very fast in our processes means we're actually going to have large temperature gradients, large temperature changes, and this in turn will affect the spatial and temporal distribution of, say, crystallinity. And so any material constitutive models we develop need to be applicable to those rates. And again, as part of that, the tooling and the equipment can be quite complex. We need to put that in, and it can be very, very expensive to do that. So typically what we try to do is put in a simplified representation of the tooling and the equipment, or if we can get away with it, put in the tooling and the equipment as boundary conditions on the piece of interest. So what are the things we really need to understand on the way in? We need to understand the crystallization melt kinetics of the material, and hand in hand with that, its thermal conductivity and heat capacity behavior. Once we've understood that, we need to understand how the matrix viscosity changes, how the fiber bed might take some of the stresses during the process, and how we model and capture intimate contact and autoadhesion between interfaces. Then, of course, we need to understand how the modulus develops, what the coefficient of thermal expansion does, and how much crystallization shrinkage we have. A really important point that quite often is not adhered to but you need, if you're going to be very systems-based and very consistent, is to realize that in a real system response, nothing is isothermal, nothing is constant heating rate or cooling rate. And so to be able to cope with any arbitrary temperature history, we believe that you've got to write all your properties in terms of material state variables. And even the change of those material state variables has to be written in terms of those state variables. So you basically end up with a formulation which is differential in form. What this means is you can integrate it for any arbitrary problem. At the moment, the two matrix state variables for thermoplastics are the temperature and the total crystallinity, so that everything is described in terms of what's the, say, CTE, the coefficient of thermal expansion, given that I know what the temperature is, given I know what the current degree of crystallinity is. Now, if this is done properly, if it turns out that we really should be tracking the crystal morphology, say we want to break it out into a transcrystallinity, which typically is the way we get crystallization around the fiber, or spheroidal crystallinity, which is what happens in the away from the fiber in the sort of bulk resin, then one can actually break that out into substate variables if you wish. Again, if you do this right, you can cope with any arbitrary temperature history, and I'm going to show you an example of that, actually a couple of examples of that in my case studies. As a side note, this applies even to viscoelasticity, as long as, again, you use a differential approach, which then makes it consistent with the rest of the framework. So let's jump in. Let's first of all think about how we characterize the material thermophysically. So again, most of the literature typically considers things isothermally or non-isothermally, whereas really a good crystallization melt model captures both. And one of the things we've noticed is that in crystallization, there's an induction time. There's a phase where you're actually nucleating the crystal. And this really needs to be captured in your models. There's not a lot of melt kinetics models out there. In fact, the one I know goes way back to the 90s by Kenny and colleagues. So we believe that to have a real good virtual material model, you need to have both crystallization and melt in there. It needs to be rate type, so it can do any arbitrary temperature cycle. It includes an induction time, and it allows for this trade-off between melt and crystallization using what we call a mass to melt curve. So the material I'm going to show you is TC1200 PEAK from Torre, which has been very well characterized. And at the end, I'll actually allude to another characterization which will be shared at the SAMPI conference. The way we do our models is that we characterize the material using a whole range of DSC tests. And we use those DSC tests to give us crystallization rates, which we then look at in an isoconversional view. So what we do is we plot the rate of crystallization as a function of the temperature here. And you can see, of course, that the crystallization rate is logarithmic. And you can see three data sets here. On the right, we have the red box squares, which are isothermal melt crystallization. We have green squares, which are non-isothermal melt crystallization. These come from basically ramps. And then on the left, we have blue diamonds, which are cold crystallization. Most material, when delivered, is partially crystallized. And as you heat it up and you go above the glass transition temperature, you will actually get cold crystallization as the material becomes more mobile. So our models capture both cold crystallization and hot crystallization, melt crystallization. And fundamentally, and in the literature, there's many forms of this equation. But basically what you say is the crystallization rate has a temperature dependence and a crystallinity dependence. Basically, there's two competing mechanisms. the more you undercool your material from a nominal melt temperature, the more the material wants to crystallize. So that drives up the crystallization rate. However, the colder the material, the less mobile it becomes. So that slows down the crystallization. So the net effect of temperature is a fight between a driving force which increases with reduction in temperature and a mobility which decreases with that reduction in temperature. That's what gives us that peak behavior in the middle. What about induction time? The induction time has a behavior where it's higher for higher temperatures. So again, lower undercooling leads to less driving force. And in non-isothermal crystallization, that exhibits itself by having a longer induction time, the lower the cooling rate. The way we deal with this is there was an empirical model proposed for induction time all the way back to the 1970s. We use that, and we then chunk it so we can do non-isothermals. And you can see here, for example, on the right, you can see induction time versus temperature, and you can see how the induction time is very small at low temperatures, but it becomes quite appreciable at high temperatures. And as an example of how good these models can be, if you have enough data and you spend enough time fitting it, on the left, we see an isothermal prediction. On the right, we see a non-isothermal prediction for a 10 CPM test. So pretty good predictions. What about our melt behavior? What we do for melt is we say at any instant, there is a desire for the material to crystallize or recrystallize. We use the model we showed you in the previous slides. And we say, but the material also has a driving force for wanting to melt. So we model that as well. And then we say, in every time step, the total crystallization is the positive crystallization less the negative melting. And then we update the crystallization for the next time step. When we do that, what we find is that we pick up, say this on the left is a comparison of experiment and model predictions at 1 C per minute. And you can see that we capture this sort of trade-off in melt and crystallization on the way to full melt. And on the right, what we can pick up is that depending on how fast you ramp, you get quite different behavior because again, the melt and the crystallization have different sort of time constants, if you will. And so the model is capable of capturing the intricacies of melt as well as the intricacies of crystallization. And that's really important because in many problems, say welding, understanding how long it takes you to melt is in some ways more important than understanding how it crystallizes, which just happens after the fact. What about thermomechanical simulation? Well, there's a whole bunch of ways that we can analyze stress development in a composite. The simplest is to use a very simplified hardening instantaneous linear elastic approach, which basically says that the modulus of the material is a function of the temperature and the degree of crystallinity at each time instant. It can do hardening behavior, but it can't do stress relaxation. The proper way of doing things, of course, is viscoelastic. For thermoplastics, you actually have to go one step up because the material actually is thermorheologically complex. And now you've got to put in even more detail to capture everything. And there's people who actually use a viscoplastic approach. What we prefer to do is to do the first 3 bullets. We characterize the material at the full thermoviscoelastic level, but often we actually exercise it by simplifying the use of the material model at the child level for this very simple reason that running a full thermoviscoelastic model is computationally very expensive and quite sensitive. It needs a lot of love and care to get it to run fully. Once you have that model for the modulus, you then also need to be able to characterize the coefficient of thermal expansion and the crystallization shrinkage. And from that, You basically time step through the problem and you predict how much stress is accumulating in the system. To really go into the gory details of how you develop a modulus model is a talk in itself. So what I really want to emphasize is this graph on the right, where we're showing you the resin shear modulus plotted logarithmically versus temperature. And what this shows is that at low temperatures, the resin modulus changes a little bit with temperature. There's a big drop when you go through the glass transition of the amorphous phase. And then, depending on how much crystallinity you have, and you can see here we have isoconversional contours from 0.1% to full partial crystallinity for peak of 33% approximately. What you see then is that you get this huge drop. If it's fully amorphous, obviously it drops to basically, well, it's not zero, but it's a very low value. As you increase the amount of crystallinity, you get more and more high temperature stiffness. And you can't actually do a test to get this. To create this graph, you have to do lots of tests and then generate this. But this then becomes our master curve that we can use in our time stepping through the problem. In similar fashion, this is the CTE of the material as a function of temperature. You can see a glassy CTE, transition through the glass transition temperature to a higher CTE, and then past that, much higher CTEs all the way to melt. That's the neat resin. We, of course, have to convert that into prepreg properties. So a huge number of steps where we're really capturing the behavior of the thermoplastic in terms of these state variables so we can run an arbitrary problem. Let's touch on weld quality and degradation. There's really two things that matter in bringing two interfaces together. The first is that the interface surfaces are rough. So the first thing you have to do is go from the initial low contact to full intimate contact. So you basically can plot a parameter, which is the true area of contact divided by the nominal area of contact, which over time, if you apply enough pressure and you go to a low enough viscosity, will go to 1. There's not a lot of DOIC models out there. So the baseline at the moment is the Lee and Springer model, which was developed way back in the 80s. And it's a very elegant little model. Basically, it says, think of the surface as a bunch of pillars which are squeezed flat, and you increase the true surface contact. And it's all driven by a flow index, which allows for both the pressure and the viscosity. So the higher the pressure and the lower the viscosity, the faster the material flows. So that gives us the degree of intimate contact. But that's not enough. We also have to get molecules to rotate across that surface. So you also need to track the degree of autoadhesion. And that, again, is said to have a similar form. And again, there's a first generation model for that, which again captures that in terms of the viscosity, which is used as a measure of the mobility of the molecules. And of course, you need to allow for the current state of autoadhesion because it'll actually slow down once a whole bunch of molecules have rotated. How about degradation? Again, there was a first generation degradation kinetics model put out by Nam and Seferis quite a long time ago. And they proposed a model that was based on mass loss in a TGA. And so again, you come up with a parameter, which is alpha D, the amount of degradation. It goes from 0 to 1. And again, there's a thermal component to it. There's an Arrhenius relationship with temperature. And this is what's typically used at the moment to come up with a upper bound to the acceptable temperature. I'm not sure that this is sufficient. and whether there are more subtle degradation mechanisms operating at lower temperatures. Maybe cross-linking, maybe some subtle chain scission. I think more research is needed. But again, the framework we use allows you to just add more models to the library for any physics that you're interested in. So let's jump in and look at a couple of examples of problems of interest, and let's try to understand them using these models. So the first one we're going to do is we're going to look at some spring-in when you're thermoforming a L shape as a sort of simple geometry. So what we did here, and this is work done by a graduate student at UBC on the experimental side, a bunch of L shapes were consolidated in a hot press at 3 different tool temperatures. Again, we're using the Toray TC1200. The laminates were previously made into flat panels, and they were a quasi-isotropic 16-ply laminate. Those flat panels, cut to size, were preheated to 390 in a furnace. They were rapidly transported to a press where there was a mold with a 90-degree shape to it. The press was closed, and the platen temperatures were held at one of 3 temperatures: a high 290, a midish 215, and a ridiculously low 105. In all cases, held for 5 minutes with a 40 bar pressure, then removed from the tool, allowed to cool to ambient by natural convection before spring-in measurements were done. So the parts were measured using a CMM, and what you see, and you can see it as an image on the right and a table on the left, the higher the tool temperature, the bigger the average spring-in. So if you pop that plate onto a 105 degrees centigrade tool, your spring-in's about 0.6 degrees. If you pop that part onto a tool that's at 290 C, your spring-in is 3.3 degrees. So a huge difference. Well, if you basically create the FE model on the left, run it in Abacus with the Compro extensions, which engages all the material models that I very quickly described to you, you time step through the process, and basically the model steps through, and at every time step says, hey, what's the temperature distribution? Based on that, what's the crystallinity? Based on that, what's my modulus? What's my CTE? How much crystallization have I got? And it calculates a stress at every point, which gets integrated over the whole cycle. That residual stress, the moment you take the part off the tool, makes the part distort. Some of it stays locked in, but that which is relieved gives you the spring-in. And on the right, you can see the corner spring-in as a function of tool temperature, and you see the experimental results from the previous table in the red triangles with the error bars on them. And you see the computer prediction, the simulation prediction for the simplest representation of the problem, which is the crystallization hardening instantaneously linear elastic model. And you can see that it captures it very well. So you look at this and you go, well, there's a lot of complexity there. How do I get a little bit of simple insight into the problem? And here's the way I like to look at it. What we're doing here is just showing you the crystallinity history as a function of temperature for the 3 cycles. What it shows is that when you do the 290C tool experiment, all the matrix crystallizes at 290C. So the material has memory 290C and below, which means that everything down to room temperature is going to show up as a CTE delta T. But if you go to 215C tool, the crystallization occurs at a much lower temperature, and now you're starting to see a big gradient through thickness, because the surface sees the tool temperature right away, whereas the inside of the specimen which, by the way, here is only 2 millimeters thick, that lags a little bit. If you go to 105C tool, things are even colder now. And so the material isn't fully crystallized until a much lower temperature, and the through thickness lag is now even bigger. And this is only 2 millimeters thick. So if you were doing this experimentally, and you did a thin specimen, and you then applied it to a thick specimen, you would be misled. Different part thicknesses are going to give you different thermal gradients, which are going to give you different crystallization onsets. And so that's where simulation becomes really powerful. This ability to understand how things interact. What I'd like to do is finish with a more detailed process simulation example, which is a follow-on from the presentation by Dr. Ali Yousefpour, where he presented the continuous resistance welding framework and the experiments done both at the NRC and at the DLR. And so our role here was to use the process simulation framework that we've developed to actually come up with the capability of doing model-based control for this process. So in this process, what you're basically doing is, rather than trying to create the whole weld in one step, you basically run a roller along your weld line and you locally energize the mesh to give you local heating, which then moves through the whole weld line. So theoretically, you could make very, very long, infinite welds, so long as you've got the whole system set up. And just as I explained at the very beginning, you ought to start with a very systems-based description of your complete system. So in this case, again, going back to our M-step definition framework, what we have is the equipment, which is the top side of the system. This is all the gory details of how you apply pressure and actually provide current to the mesh. Then you have the welded substrate, the neat film, the heating element, that's the shape, the part. And then you've got the tooling, which is the substructure, including the insulation, conduction blocks, and spacers. So here you are. This is what the system looks like on the left in real world, in the virtual world. Here's the weld itself. And just to understand the process, what happens is, as the roller moves along, you get a local current flowing, which is this yellow line here. And as a result of that, you get local heating, which shoots up. And then, of course, once the roller's gone past, the temperature keeps dropping. The definition of the M-step here, we really went into great detail here to prove or showcase the approach. And what you're basically doing is defining all the attributes for each part of the physical system. And one really important issue here is that you've got to treat the interface as its own material, because as it compacts, as it goes to full intimate contact, the properties of the interface can change. So then you've got your standard materials, which have to be characterized both thermally and in this case electrically, and the same for the interface material. So a very systematic way of defining the whole system. Looks a little bit overwhelming, but actually it's very, very methodical. It's really a checklist. And then we go in and we apply that to the model. And again, we're going to run this as a coupled thermal-electrical FE analysis in Abacus. So we take half the problem because there's symmetry, and we mesh that. And for the electrical system, we put in the features that matter, basically heating element and the conduction blocks. For the thermal model, we actually put in a lot more detail because, of course, the thermal problem engages a lot more of the system. The welding physics is basic. It's Ohm's law in action, Joule heating. the key of the electrical submodel is to capture the gory details, because what happens is that you actually get two important things. The way the voltage is applied as it rolls across the blocks means that there's actually a situation where only one block is engaged or both blocks are engaged. And the other one is, how does the heating element basically distribute the current based on its mesh, its properties. And basically, we then, based on that, come with a modeled current history that we apply as our boundary conditions. The heat transfer melt crystallization problem is a classic conductive heat model. And in doing that, we engage with the melt kinetics, which basically says as the temperature goes up, it will melt, and then later on it will crystallize. And again, here we're using the model that I just showed you earlier. So basically what we have is a transient 3D heat transfer model. The power density comes from the electrical model. And we have convective boundary conditions on the exterior of the tooling. So we've got a boundary condition on this side here. We have a upper boundary condition. And based on that, we can run the problem. So now what we're going to show you is the current density is shown here, and that leads to a temperature profile above. And so for 1 point, you can see that you have the total electric current in yellow. You've got the local power density at point N, this point here in blue. And red is the temperature at point N. Key things to observe from this are that the power density drives the heating, that it's a non-uniform temperature distribution, and this is really important. Peak heating occurs behind the roller position. So if you're interested in doing control of this system, you can't use a classic PID approach, because guess what? By the time you realize you're too hot, there's nothing you can do about it. So you need to forecast what's going to happen, and that's where model-based control becomes important. How good is the predictions? Well, the predictions are pretty good once you fine-tune quite a few parameters. We input a current that you can see on the left, a current comparison for a few tests. In the middle, you can see some temperature predictions from some TCs that were put in the center of the weld line. And here's an example of a prediction for a TC on the edge of the weld line, because there's actually quite a big temperature variation across the width. And so the model actually does a very good job of predicting the weld temperature history with high accuracy. One of the lovely things about a model is you can do a parameterization and see what really matters. So what we did was we looked at the thermal model parameters and we changed everything that mattered. And what we discovered was that, for example, you can change the heat transfer coefficients on the surfaces by an enormous amount, and it makes very little difference. Playing with the specific heat capacities can have a bit of an effect. And in fact, what we've discovered is that it's really important to get your inert properties right. But the thing that comes out of this is that thermal parameters are really low moderate impact. What is very important is getting your electrical model right, which in turn means that in practice, in production, this is what you really want to control. How your mesh behaves, how your blocks behave, makes a huge difference. The mesh conductivity is a critical parameter. The block contact behavior is also very important. So in terms of control, the model tells us what you really want to fuss about is your electrical parameters. So then what you can do is you can take these temperature histories and you can, for example, here what I'm showing you is the importance of actually two things. Your inert properties, if you use temperature-dependent inert properties, which the literature does in places, what you discover is that your model predictions are off. The red is inert independent. The blue is inert dependent on temperature for both the center and the edge. There's an interesting side conversation that David Leach will be interested in, which is that one of our students looked into the pedigree of all the material properties in the literature, and they basically all go back to a couple of papers, all the way back to Blundell. So you need to put in really good temperature-dependent inert properties, but look, putting in the transformation properties, in other words, the heat due to melt or crystallization, makes a tiny difference. And the reason for this is there's not a lot of material that melts and crystallizes, so avoiding that is not an important issue. So temperature dependency, really important. Because melt crystallization doesn't do much to the temperature profile, it means we can run a decoupled model. Run the thermal model inert, then use that temperature prediction to predict melt crystallinity. And that's what you see here. We took the temperature predictions, and then we ran it through the Compro material models to predict the melt and then the crystallization. And here you're seeing just 2 points at a random position for the edge and the center. The edge melts first, crystallizes first, because it's ahead in its temperature profile. The center melts later, crystallizes later. So how useful was this? Well, I'd like to finish with this slide, where we see 3 tests. A test where the system was run very slowly, and what you see is when you tear the weld apart, you've got really good melt everywhere. This is the start, this is the end, but in the center section, you can see that you've got really good weld. Speed it up just a tad, 0.85, you're starting to see hints that the melt was not complete. Go to 1 millimeter per second, and what you see quite clearly is that you did not melt, and therefore you have obviously a bad weld. How well does the model do? Well, here's the model predictions. Blue means full melt, red means nothing happened. The colors in between mean partial. What you can see is that the model captures a very good weld, starts to indicate that you're starting to get a bad weld, and shows quite clearly and very faithfully the fact that you did not melt at all in the center. You melted at the edges. Remember, it's hotter at the edges, but you did not melt in the middle. With that, cognizant of the amount of time, I'd like to put in a plug for SAMPE in Long Beach, and to share that the material model you saw here was TC1200 Peak. Convergent has recently finished a project with Torre on their LMPAK TC1225 material, and that's going to be shared in a presentation at SAMPE, which, as you saw, has a huge number of thermoplastic presentations. So please do join us there. So to summarize, much like thermoset matrix composites, here you still should always include the relevant features of the system. Material behavior characterization is really important over the process range of interest. We believe you should put in both crystallization and melt kinetics, and it should be in a differential form so it can do any temperature history. At the moment, we track everything in terms of the state variables of temperature and degree of crystallinity. In the future, that may need to be a bit more complex. And at the moment, if you have a different fiber or fiber sizing or fiber volume fraction, you have to do enough tests on that configuration to be sure that the models apply, or modify the models so that they apply. At the moment, we can't put those in as independent state variables. Once characterized, these models actually provide valuable insight, optimization control, And you're starting to see an increasing number of case studies to validate this, thus giving you confidence that they're worth using. Look, there's always much more to be done, and it's really nice to see that there's a lot more being done in the literature. It's picking up rapidly. It's starting to catch up with thermosets, which actually have had more applications of process simulation. And it's a bit of a trite thing to say. The key is to capture all the physics, but no more, because the problems can become quite complex otherwise. With that, I'd like to finish off by again acknowledging my coworkers, our collaborators, and again, acknowledging that everything I presented to you today was unavoidably biased to what we've done. With that, I'd like to thank you, and if there's time for questions.
Thank you very much, Anoush. Thank you. So I encourage everyone to please put your questions in the Q&A. We already got some questions in. So the first question, for the L forming at different temperatures, can you predict the volumetric change, therefore springing, due to crystallization alone versus due to CTE from the tool temperature?
Absolutely. I mean, you're tracking those as contributors to the total effect. And I can't tell you off the top of my head what the contributions were, but I believe the bigger dominant contribution is the coefficient of thermal expansion, the thermal effect. But the model tracks everything.
Okay, thank you. The next question, do you have a physical interpretation of the term induction time? I didn't see it in the M step though.
So the induction time, really, it's the nucleation of the crystals. If you go, the metals people have done this to death. If you have a melt, there needs to be a little island where the crystallization starts, and then the crystal grows from that. In fact, this is something for semiconductors is done very, very elegantly. And so if you've got a pool with no imperfections, no impurities, it can actually take a long time for the crystals to start growing. If you have fibers in our case, then the fibers are a lovely surface from which crystals grow. So induction time is very much the start of the crystallization process.
Thank you. The next question, a very interesting and informative talk. Could you please comment on the accuracy of available intimate contact and interdiffusion models?
Great question. I would defer to some of my more experienced colleagues on our team. My comment would be that there is not a ton of data out there at the moment to give us high confidence. Typically, what's happening in practice is you just allow yourself enough time to get that. In the case of the weld, for example, we discovered that by the time you had melted, that was enough time to get intimate contact and autoadhesion. So, for example, one question would be, given that you have to melt, is that enough time to get intimate contact? We did a project, again, with NRC quite a few years ago on in situ AFP. And there, again, sorry, I'm rambling here. I think the answer is we would love to have more data.
Okay, thank you. For the next question, how is warpage factored in?
Great question. If you run the models in full detail, what happens is you get a corner contribution, which comes from the geometry at the corner. But then you can actually get two things happening on the flanges. One is you can actually get tool part interaction. And what that does is it gives you stress in the first layer, which then gets sheared out through thickness. And the other one is that the corner spring in actually gives you a bit of a warpage as well. Both of these are mitigated by shear deformation. So if you do a short, fat flange versus a long, thin flange, you'll get totally different amounts of warpage. And again, a properly calibrated material model which captures that shear behavior, a model that captures the friction at the tool surface, you should be able to capture that warpage very well. Whereas an L there's people who believe that a C channel is the best way to validate a model for warpage as opposed to an L angle.
Thank you. The next question, do your models allow for flow of material from one element to another, or is this not important to model?
No, so if you were doing infusion models, then that matters. So where the models I've been showing you are not infusion models. There are infusion models. What we have is very small amounts of flow, for example, to close the element. Sorry, to close an interface. And there you don't need to, you can allow the element to distort as opposed to need to move material from one element to the next. So the models we're doing are basically saturated flow models where the amount of movement is small.
Thank you. The next question, any influence of thermoplastic composite consolidation state before heating up / cooling down on residual stress buildup?
Big question. I'll start off by saying that the very first thing that happens is if you put down a whole bunch of layers on top of each other and it's unconsolidated, and this is true for a thermoset that's not debulked or a thermoplastic where you've got a bunch of sheets, each one of those interfaces is a thermal contact resistance. So the temperature history of an uncompacted stack is quite different from the temperature history of a compacted stack. So that is the very first step. Then, depending on whether you fully melt everything, which basically means the material loses its memory, or not, all of that could snowball into something that then shows up in residual stress. So my way of looking at a problem like that would be to very methodically use the models and modeling approach to look at whether it will have an effect or not. And sometimes it might. Very often it might not.
Thank you. So we still have more time for questions. So if anyone else has any more questions, please feel free to ask them in the Q&A. Okay, there's more questions coming in. Next question, would it be possible to predict the weld time needed for a certain material to reach a definite degree of intimate contact?
Given that you've characterized the material, I don't see why not. There's two parts to that. There's melting it or heating it up. You don't necessarily need to melt to get intimate contact and then, well, no, let me retract that. You need to get to a high enough temperature that your viscosity is low enough that you can actually get the degree of intimate contact up and to get the autoadhesion. So yes, I think if you characterize your material, there's no reason why you can't predict that.
Thank you. The next question, how do you characterize the fiber reinforced tape material for very high cooling rates with the aim to extract the crystallization kinetics?
Sorry, can you repeat that?
Yes. How did you characterize the fiber reinforced tape material for very high cooling rates with the aim to extract the crystallization kinetics?
You're really at the mercy of the equipment you own. So there are DSCs which can go very fast. We're actually waiting on one right now. We're very excited. And so these can do controlled cooling rates at many hundreds of degrees C per minute, or they can even do ballistic cooling rates at even higher rates. So basically, you need to generate the data. Once you have the data, model fitting is a very standardized activity now.
Thank you. For the next question, does stress-induced crystallization affect the induction time model?
Great question. Our models don't have that in there right now. We've had team members who've said it should be there. One of the rules of modeling is if you put in absolutely everything that could possibly happen, the models can become incredibly expensive to calibrate and to run. So you really have to work backwards from observations where you go, something matters, and then you put that physics in. If the person asking the question has any data or any case studies or any hints that this is important, I'd love to hear about it. Within the team, I'm not the thermoplastic expert. I have to say that, but we'd love to hear about that.
Thank you. The next question. These models have a large number of properties or parameters. Given the sensitivity of some of these, do you foresee a need for inverse identification of some properties from calibration tests to get actual properties?
So we're touching now on sort of the data sciences and machine learning and AI and all that. Absolutely. If there's ways of identifying what matters, then we should use them. So for example, our next generation of models will be probabilistic. So you actually build in your confidence in the material models, in your boundary conditions. And then you run those backwards, forwards. These are all tools that help us minimize effort, increase confidence. So I purposely didn't touch on that because that's its own talk. But absolutely, any approach that helps get value out of these models.
Thank you. The next question, are measures springing angles from the L shape time dependent? Wondering about long-term dimensional stability.
Really good question, and ties into the material doesn't really think it's being processed and then it's in service. It's a continuous history. So things we've been doing, we have a graduate student at UBC who's done a lovely job of showing that as you absorb moisture, the transient levels of moisture actually give you dimensional change. Then you have viscoelastic effects. Then if you're at high temperatures, another student's been looking at physical aging. So there's lots of other things that can actually cause dimensional instability or dimensional change over time. Again, I would go back to, you really got to look at your service conditions. You've got to look at how much margin you have in your design and work backwards to whether you should worry about it or not. Now, as an academic, you love to look at these issues. And I don't know who's asking that question, whether it's an academic, in which case, yeah, these are lovely questions to look at, or if it's somebody in industry who's perhaps asking, should we worry about it? And there's two different perspectives in answering that question.
Thank you, Anoush. And there's still more questions that came through, but unfortunately, we're already at noon Eastern or 9 a.m. Or another time, wherever you are. So we have come to the end of our webinar. So if you have any questions and if you're okay with it, Anoush, they can contact you for any follow-up because unfortunately we ran out of time. But I would like to thank you again for such a great webinar and for giving us the time to share all of this information. And thanks to everyone who attended as well.
Thank you for giving me the opportunity.